In this video, we'll see how to perform insertion in a heap. The insertion should be done in such a way that both the structure property and the heap order property are satisfied after the insertion also. Now suppose we have to insert a new key in a heap of size n. Then first the size is increased to n plus 1 and then the new key is inserted at n plus 1th index of the array. This is the next leaf node of the tree. So the tree remains complete binary tree after insertion also. Let's take an example. This is a heap of size 12 represented by this array. Now we have to insert this new key in this tree. So the size is increased to 13 and the new key is inserted here at 13th index of the array. We can see that this is the next leaf node of the tree. So the tree remains a complete binary tree after insertion of this key. And so the structure property is not violated. Now let's check the heap order property. This 42 is less than 80. So the heap order property is violated. Now to restore this heap order property, we have to move this key upwards in the tree and place it at its proper place. We'll do this by performing a procedure called restore up. Now let's see what this procedure is. Suppose k is the key that is violating the heap order property and has to be moved up. So we'll perform restore up for key k. We'll compare k with the key in the parent node, and if the parent key is less than k, then we'll move the parent key down to the node where k is present. After this, we'll try to insert k in parent's place by following the same procedure of comparing with the parent node and moving the parent key down. This procedure will stop when we get a parent key that is greater than k or we reach the root node. Now let's understand this with the help of examples. This is a heap of size 12 and we have to insert this new key 80 in this heap. So first the heap size is increased to 13 and this new key is inserted at 13th location. Now we have to perform restore up for this new key. So we'll compare this key with the key in the parent node. This parent key is smaller, so we'll move it down and now we'll try to insert 80 in parent's place. Now this is the new parent key. So we'll compare this 80 with this 55. 55 is smaller, so we'll move it down and now we'll try to insert 80 in this place. Now this is the parent key. So we'll compare 80 with this 85. 85 is bigger, so we'll insert 80 here. Now suppose we have to insert this key 92 in this heap of size 9. So first the heap size is increased to 10. This new key is inserted here at the 10th location. Now we have to perform restore up for this new key. So we compare this key with the key in the parent node. The parent key is smaller, so it is moved down. And now we'll try to insert the key here. Now again, this key is compared with the key in the parent node. The parent key is smaller, so it is moved down. And we try to insert the key here. Now it is compared with this key in the parent node. It is smaller, so it is moved down. And we'll try to insert the key here. So now we have reached the root node. So we have to stop and insert the key here. Now suppose we have to insert this key 60 in this heap of size 10. So first the heap size is increased to 11 and the new key is inserted here at the 11th location. Now we have to perform restore up for this new key. So we compare this key with the key in the parent node. The parent node key is bigger, so there is no need to move this key up in the tree. Now let's see the runtime complexity of insertion operation in a heap tree. For insertion, we have to move on a single path from a leaf node to the root node. So if h is the height of the heap, then the runtime complexity of insertion becomes order of h. And we know that height of a complete binary tree is ceiling of log base to n plus 1. So this becomes order of log n. Now the worst case occurs when the key to be inserted is the largest and it has to be placed in the root node. And the best case is when there is no need to move the key up. In our examples, this was the case when we inserted key 92 and this was the case when we inserted key 60. Now let us see the program for heap tree. This is the class heap. This is the list that is used to represent the heap. This n denotes the size of the heap. In this constructor, we are allocating this list and initializing this heap size to 0. In 0th index of the list, we have placed this sentinel value. All values in the heap should be less than this value. And this argument here denotes the size of the list that is to be allocated. Now this method will insert this key value into the heap tree. First we increment the size of the heap, then we place the key value at the nth index, and then we call this method restore up with argument n. This method restore up will place the new key at its proper place in the heap. So now let's see this method restore up. This I is the index of the key that is violating the heap order property. K equal to AI. So this K is the key that is to be moved up. Now first we are calculating the index of the parent key. Now in this while loop we are moving the parent keys down, and we will stop when we get a parent key that is greater than or equal to this key K. So this statement is moving the parent key down, and in each iteration we are updating the values of I and I parent. After this loop stops, this key K is placed at the ith index of the list. Now let's take the case when the key to be inserted is the largest key and is to be placed in the root node. In that case, in the last iteration of this while loop, I will be 1 and I parent will be 0. And we placed a very large value at the 0th index of the list. So this condition will become false and the loop will terminate. And this key K will be inserted at index 1 of the list. If we don't put the sentinel value, then we'll have to include this additional condition in the while loop to stop the loop in the case when the new key has to be inserted at the root node. So by placing a sentinel value at index 0, we have avoided checking of one condition per loop iteration.